Modern systems most constantly find the absolute majority element across millions of incoming server logs, sensor readings, and user votes. A common instinct is to use a hash table to count frequencies. But as data scales, this approach requires O of n space, eventually exhausting memory and crashing the system. Sorting the data is equally impractical. An O of n log n time complexity is simply too slow to keep up with a live, infinite data stream. These constraints mirror the reality of 1981, when algorithms processed data from sequential magnetic tapes. These machines only allowed a single forward pass with virtually zero memory. Solving the modern data bottleneck requires that 1981 mindset. We need an algorithm that processes infinite data in a single pass with strictly constant O of 1 space. To achieve constant space, we have to abandon the instinct to count and store the data as it arrives. Instead of simply tallying the elements, we force them into a zero-sum game where they eliminate each other. This is the Boyer-Moore voting algorithm. The solution isn't found by counting the living, but by seeing who survives the slaughter. The system uses two variables, a candidate slot and a counter. An identical element reinforces the candidate, adding 1. A different element triggers the conflict rule, annihilating 1 life. If the counter hits 0, the candidate dies, and the next element claims the throne. This loop continues relentlessly, element by element, until the data stream ends. By tracking only a single candidate and discarding all non-matching pairs immediately, the algorithm traverses millions of data points using 0 extra memory. Why does this destructive method guarantees that the correct answer survives? A true majority is an element that appears strictly more than n over 2 times, making up over 50% of the dataset. Even if every minority element teamed up to annihilate a majority element, the majority mathematically has enough troops to outlast them all. By the end of the stream, the final survivor must be the majority element. Structural logic replaces the need for brute force storage. But there is a classic technical interview trap. What happens to the algorithm if the data stream contains no majority element at all? Take a fragmented array like A, B, and C. A enters and becomes the initial candidate. B arrives and annihilates A, dropping the counter to 0. This leaves the slot open for C to claim the throne and survive as the data stream ends. The algorithm confidently outputs C as the winner, even though it only appeared once. Without its base assumptions, the algorithm is blind to reality. This failure is a consequence of the information theoretic lower bound. You mathematically cannot confirm a majority in a single pass without storing data. Senior engineers resolve this with a mandatory safeguard, the verification pass. This process takes the surviving candidate, sweeps the array one final time to count its actual occurrences, and verifies it definitively crosses the n over 2 threshold. Engineering mastery demands understanding the absolute limits of a mathematical optimization and building the necessary safeguards to prevent real-world failure.